Now use again the mathematical analogy we already know. So in non-relativistic quantum mechanics, we already know the following result, that x hat p hat is equal to I h bar implies x p x prime, the position space representation of the momentum operator is minus I h bar del x of delta x minus x prime, where x state is the position is the eigenstate of x operator. So this entire thing has been now constructed in on the QFT side, and I have to just use the same logic that this is the logic. There is a derivation for it. I will not do the derivation in QFT, but use the same logic. This is a theorem. Use the same result to write down this equation directly in QFT. So therefore, applying the same result in QFT, what I should write is okay. So this is of course at a formal level, at formal level, of course, that this quantity, analog of this quantity, must be minus I h bar del phi tilde of p acting on delta function. Okay, so how am I applying this? This x is the eigenvalue corresponding to x operator, which is conjugate to p, right? So that is how this p and that x is related. So this is my momentum operator, and the conjugate position operator is phi hat of p. If this is minus p, then the conjugate position operator is phi tilde of p, and that's why I'm taking derivative with respect to phi tilde of p. So this is important. This is minus p and this is plus p. That way it has been defined. Okay. And you can further extend this result to the calculation of phi tilde minus p psi is equal to integral d phi tilde prime phi tilde minus p phi tilde prime psi phi tilde prime, and this is equal to minus I h bar integral d phi tilde prime del phi tilde p delta phi tilde minus phi tilde prime psi phi tilde prime. Now you use the usual manipulation. This derivative with respect to phi tilde can be converted to derivative with respect to phi tilde prime. at the cost of an extra minus sign, and then derivative with respect to phi tilde prime can be you can do integration by parts to apply this on this with a cost of another additional minus sign. So these two minus signs will cancel, and the result is minus I h bar del del phi tilde p of psi phi tilde. Okay. So this is all about the Schrodinger representation of the QFT, and now I will give an exercise to apply this framework to the particular case of Klein-Gordon theory. So exercise Klein-Gordon theory. So here the action is given by minus half integral d dx del mu phi plus m square phi square, and then you can define creation annihilation operators. By relating phi tilde hat t p with this h bar by 2 omega p a p e to the power minus I omega p t plus a minus p dagger e to the power I omega p t. Then show that the conjugate momentum in momentum space is given by minus I root over of h bar omega p by 2 ap e to the minus I omega pt minus a minus p dagger e to the power I omega p t. And ap aq dagger is equal to delta p minus q. Okay. Then the vacuum state is ap acting on vacuum equal to 0 for all p. So now the exercise is to find, number one, vacuum wave functional. Psi 0 of phi tilde by definition is phi tilde 0. And number two, condition for normalization, which is this. Okay. Yes. So that finishes this discussion of Schrodinger representation of quantum field theory, and the mathematical analogy that has been used to find this. You should think about it, especially this one, and try to convince yourself that all of it makes sense just by following the usual non-relativistic quantum mechanics description in the Schrodinger theory. Just following those things and applying this analogy with a discipline, and one arrives at all these equations and these results, which finally enables one to find the wave functional for the vacuum state of the quantum field theory, Klein-Gordon theory. And if you have any question, you should clarify me when we meet. Okay.